Prem, will the chat questions come in here?
I don't know, Kannan. This is the first time I'm actually using this.
Yes, they will. So the ones from YouTube, well,
Also, I will also be able to see the chat questions. We are already live.
Yeah, let's go live. I think we've been live for a while. I was just waiting for 9:30 or so Pacific time to get started. But yeah, why don't we kick things off? Hello, welcome everyone to the next episode of the YugabyteDB Friday Tech Talk. And now this time we're streaming through the StreamYard platform, which I believe encompasses the LinkedIn Live, YouTube Live, and so on. So there are multiple ways to engage our audience, and please let us know if this different format there's any confusion or any changes that you'd like to give us feedback on. But please do keep your comments and all of those coming in as usual. And then let's jump right in. Once again, I'm Kannan, Muthukkaruppan, one of the co-founders at Yugabyte. It's my pleasure to welcome you all to today's episode of the Friday Tech Talk. And we have Prem with us today, who's given multiple talks earlier on this series. Pleasure for me to welcome Prem, and please take it over, Prem.
Thanks, Kannan. Hey everybody, I'm Premkumar, technical evangelist at Yugabyte. Hope you're all having a great day. Today, we are going to discuss how to model your data for a distributed database like YugabyteDB. Remember, data modeling is a very vast topic, and this is just an introduction. We'll first look into what data modeling is all about and understand why data modeling is different for distributed databases as compared to monolithic databases. We will also delve into how table data is distributed, and I'll explain the significance of this a little later. We will explore the importance of primary keys and look into designing the right index for your queries. If time permits, we will see how table partitioning is useful for managing large volumes of data. First, let's look into what data modeling is all about. A database is used to store data, but the business data has to be correctly represented with proper schema designs. You have to correctly carve the various entities into table schema and define the relationships between them. For example, if you are designing an e-commerce system, you have to decide which information should be stored in the customer table, products table, and how the orders table relates to both customer table and the order table, products table. You need to design the schema first by understanding the common access patterns. So once you come to consensus on the access patterns, you have to choose the best indexes for fast data retrieval. You will have to decide if you are going to partition your data or not. So thinking about these and understanding these quite well will help you define the various constraints like primary keys, foreign keys, and unique keys. Most people would have designed tables and indexes for monolithic databases like MySQL or Postgres. When creating tables and indexes in a distributed database, you need to be aware of certain things. Let's look at each of them. Firstly, in a distributed database, there are many nodes, and the table data will be spread across these multiple nodes. Even though the applications can connect to any single node or many nodes, reads and writes most likely will span multiple nodes. Because of this, network latencies have to be factored in. Also, you could have placed some data in certain geographies and cross-geo, cross-region latencies could be high. Just to show you how YugabyteDB is similar and at the same time different from a monolithic Postgres, take a look at this visual. Yugabyte uses the same query layers just like Postgres, and so queries look the same, but the storage layer is spread across multiple nodes. So reads and writes have to be coordinated between nodes. This is a very, very important factor to remember when you model your data for a distributed database. As we just discussed, in YugabyteDB, the table data is spread across multiple nodes. It's absolutely important for you to understand how your data is distributed so that you can model your schema optimally. Starting is how data is distributed and stored sorted. Let's look at two of the starting screens that YugabyteDB supports. First here is hash data. The data here is distributed based on the hash of the primary key. The table data is split into tablets, and each tablet owns a hash range and stores the keys that falls into that range. The rows are ordered on the hash of the primary key and not on the data type sort order. This is great for point lookups and gives a good distribution. With growth in data, the table automatically splits into more tablets as needed. And tables can also be pre-split during creation. Here, I have a table. I don't know if you can see my mouse. So, things not sharing my mouse. But so we have a table here with names.
You're not able to see the mouse.
I don't know what setting is that, so I'm not going to mess with settings right now. But
No
so you have it on the screen. You have a table with names, and if you notice, each of the tablets have their own hash ranges. Names go certain rows with certain names go to certain tablets. That's because, for example, the hash of Felicia and hash of Jordan could actually fall into the same tablet at T1. Next, we are going to look at range sharding. In a way, if you can think, YugabyteDB is actually a purely range sharded system. Either we range shard on primary keys or hash of primary keys. So in the case of range sharding, each tablet owns a primary key range, not the hash. Keys are globally ordered on primary keys. So because of this, contiguous keys are together. For example, 1, 2, 3, 4 may be in the same tablet as they are stored in the corresponding data types order, sort of. Typically, data could start growing in one tablet before growing into another. This is great for range lookups and point lookups. So that's it. So take a look at this visualization. It's the same table with table of names. Now you have Andrea and Henry fall into an A to H range owned by T1 or node 2. So because T1 owns A to H range, automatically Andrea and rows with Andrea and Henry will be stored in T1.
Prem, just a audio or a technical question.
Sure.
Like, is there like an echo at when you're talking? The sound quality is okay, but it's not as clear. Do you feel a similar thing when I'm speaking?
I don't think so, but let's see. Audio. Reduce. Echo pattern or echo cancellation. This is good. This is better.
You just say a few more words.
Hey, this is Premkumar.
I think it's fine. Yeah, it's not like very. It's I would say 90% or so. It's fine. Yeah, let's keep going.
So to summarize, as no
Yeah, I
one
think one of the audience said there is an echo when you're speaking, but not from me. So
okay, all right. So let me. Okay, I turned on echo cancellation. Is this better? Hey, this is Prem.
I think it's fine. Yeah.
It's fine? Okay. Sorry. So to summarize, sharding, hash sharding has no ordering of rows, but gives a good distribution. It's great for point lookups, especially when you know exactly what you're looking for. In the case of range sharding, rows are ordered on the primary keys. It's great for range lookups and point lookups, like k equal to 100 and k less than 100. In both the cases, tablets will split as data grows. Understanding
So
data.
Prem, sorry to interrupt you again. One suggestion was people are saying there is an echo. So is it possible to try without the headphones, just straight up on your laptop, or?
Sure.
But we can all follow what you're saying, but it's that the clarity isn't like, yeah, the usual one. No, now you're on mute.
Is this good now?
Yeah, really good.
Yeah, really good.
But oh no, now I can hear.
Oh, you can hear
Do
your.
you need the
You need the
headphones?
headphones. Actually, I'm not using my headphones.
Okay.
Okay.
Hello.
Hello. Hey, this is
But I'm
Premkumar.
but I'm getting an echo back. Whatever I say, it's repeating back.
Okay, how about now?
It's good.
Is this good?
Yeah,
All right, we'll go.
fully clear.
All right. All right. To summarize, sorry about that glitch. To summarize, hash has no ordering of the rows, but gives you good distribution. But again, range sharding, it's great for range lookups and for point lookups. It's very critical that you understand how your data is distributed, because it's very critical for very important for modeling your data. Let's look at some sample data. So this is the data set that we are going to use in the following slides for illustration for different concepts. It's a census data set which contains information about people living in different zip codes. We have name, age, zip code, and whether the person is employed or not. And in this data sets, multiple people can have the same name across zip code and ages, just like normal. First, let's look at primary keys. Primary keys is a column or a set of columns that uniquely identifies the row. Let's look into this deeper. Primary key, as I said, is the unique identifier for the row. They should be chosen based on the most common access pattern, typically suited for user ID, order number, UUIDs, etc. If not, this is very important, if not explicitly specified, YugabyteDB will automatically generate an internal row ID as primary key. This is not visible to the user. So always remember to add a primary key when you create the table. That's because if you define a primary key after the data is loaded, the whole table has to be reordered and could take a lot of time depending upon the data size. Now let's look at the structure of the primary key. The first set of columns are the sharding columns. And those sharding columns define how the table rows are distributed. The second set of optional columns are for clustering, which define how the rows within a shard are ordered. Let's understand these with some examples. Let's create a table for the census data and set the primary key to ID. Hash sharding, we are going to start with hash sharding here, and so that we can look up the person's name, person's information based on their ID. Here, data is distributed based on the hash of the ID. You might have to look up by the name, but we will use an index for it. That we'll look at it later. You can see here that the person's information is almost randomly distributed across different nodes, but the mapping of ID to tablet is deterministic. So when looking for an ID, the system exactly knows which tablet to go to and fetches the right data. Now for range sharding, let's consider a time series like scenario where you want to store the rows ordered by ID. This scenario is based on date and time columns, but for this example, I'm going to stick with ID. ID is usually a monotonically increasing number, and let's assume that as we insert data, we are going to explicitly add a monotonically increasing ID. So you choose range sharding when you want to retain you can choose range sharding when you want to retain the original ordering of data. Let's see how data is distributed when you range shard on ID. So as the rows come in, the data is stored sorted on ID in ascending order as defined in the primary key. The data is already coming in ordered fashion. As I said, ID is a monotonically increasing number. The data grows in only one tablet, as even though there are other tablets. This is a significant key difference between hash and range sharding, but this is only a corner case. But I just want to point that out. Especially this is a concern when the data is coming in an already sorted manner of the primary key. If the data is not coming in a sorted fashion, then it's not even a concern. We will later see an example of this. Even though you have 3 nodes, you'll be inserting data in one tablet. So as the tablet grows, even here, the tablet will split. Now let's see how we can keep rows with the same name together, because previously the data was distributed based on ID. Say you want to store the information of people with the same name in the same tablet. This way, when you look up for a name, it will go to one tablet. So basically, this is data modeling in a distributed database. So you want to understand where your data is stored, and then you easily go and help the system to go and fetch the data quickly. For this, you have to distribute your data based on name. You have to specify the name column as the sharding column. But because name is not unique in our data set, that's because multiple people can have the same name, you need to specify one or more additional columns as a part of the primary key. This should be in the clustering part and not in the sharding part. For the people with the same name, rows will be sorted on the ID. Here you can see that all Michaels are stored in one tablet, T2 in node 1, and all Susans in node 3 are stored in tablet T3. If you notice, within the people with the same name, the rows are ordered based on their ID. That's because we have specified ID in the clustering part. Now let's see what happens when you range shard on name and ID. Primary key has to be unique in the same way, just as we discussed in shard. You have to add ID in the scenario because name is not unique. And your entire data will be distributed on name and ordered on name.
And then,
Yes,
yeah. So in the previous example, I just wanted to make a few points. So you said, yeah, the entire data will be, ordered by name, and within entries that have the same name, it will be ordered by ID, kind of the next level of sorting. And this kind of a composite primary key where you see multiple columns inside, it's a pretty common pattern. For example, you may have a retail, you may be modeling data for a retailer where you have orders, and orders have line items. An order may have like 5 items, like a shopping cart. So a good primary key for that use case might be order ID followed by the line item number, so that all data corresponding to a particular order is near each other, right? Like in that left to right order. And just thought I'd give another example of the same pattern.
Thanks, Kannan. So as Kannan said, now the rows are ordered on ID within the same name. Oh, so one thing to point out, even here, even as the data comes in an increasing order of ID, they will go into different tablets because you have distributed the data based on name and not ID. So it's very critical. Now, to summarize, choose your primary key carefully, as it is the most important part of your data model for your table. YugabyteDB will automatically insert a hidden row ID if primary key is not specified. Remember to specify the primary key when creating the table, as changing it later can be expensive. Keys with the same sharding criteria will end up in the same shard, and clustering columns define the ordering within the partition. I'll try to move a little bit fast because we're short on time. We looked at primary keys with which we can look up data, but what if we need to look up some other data based on other criteria than the primary key of the table? You can always do that. The SQL queries will work, but it will be quite slow. Here's where indexes come in handy. The purpose of an index is to speed up setup queries. Indexes are internally treated just like tables. They are designed internally like tables in YugabyteDB. And the data distribution is also very similar to like tables. Multiple indexes can be attached to a table for speeding up different types of access patterns. But remember, writes can become slower as each write has to update multiple indexes. Just like what we saw in primary keys, indexes have partition and clustering parts, which define the data distribution and ordering within the partition respectively. Additionally, if you can store more columns in the index itself to save a trip to the table using the include clause. That's called a covering index. We'll discuss it a little later. Now consider a query like select ID from census where zip code equal to 94085. So our primary key for our table is ID. This query will scan the whole table. That's because the query executor does not know which rows have a zip code 94085. So this could be very slow for a large table. So to speed up the lookup by zip code, we add an index on zip code as this: create index zip name on census zip code. So it could be by default. I mean, we are going to move into range sharding by default, but immediately whether it's range or a hash, the performance is the same. Now the data of the index is distributed by zip code. So the same zip code data will be stored in the same tablet of the index. Remember, these tablets of the index tablets are quite different from the main tables tablets because they are completely different concepts. But now, when you want to look up on zip code, it will be very fast. But remember, the index currently stores only zip code. If you have to fetch more columns in your select query, the query has to go to the main table and fetch. To summarize, when you have a query like with an equality clause like zip code equal 94085, partition your index on that set of columns. This way, the query will touch one tablet or very few tablets. The lookups will be very fast, great for range scans too. So when the query has columns that are not in the index, just as I mentioned before, even though it uses the index, it has to go to the main table to fetch the remaining columns. Let's see how we can avoid them. Here, we are querying for the name when zip code is 94085. By the way, 94085 is our headquarters zip code. The rows with that zip code will be identified quickly with the help of the index. But the index does not have the column name, the name of the person. So the query executor has to go to the main table to fetch that column information. In a distributed database like YugabyteDB, this can be expensive as the table and index could be in completely different nodes. So to avoid that trip to the table, we can store the column name in the index itself using the covering part, using the include clause. This way, the query will end up reading just from the index and not go to the table. This is also known as index-only scan. So if you do explain analyze on the query, you will see index only as an output there. So to summarize, when creating an index to speed up a query, add all columns in the select clause to the covering index that are not in the part of the sharding. So this makes the query run faster with an index-only scan. But you have to remember, as you store more columns in the index, you are trading space for performance. Now let's look at data ordering.
So yeah, that's a good point, Prem. So for infrequent queries, it may be okay just to take the latency hit of doing a second lookup on, going to the index first, getting the pointer to the entry in the main table, and then doing a second lookup on the table. But for frequently accessed queries, and if latency is very important, this trade-off may be a good one to duplicate the necessary columns both in the index and the main table. The system is automatically doing that for you when you use that include clause syntax in the index. And yeah, you rightly pointed out, this is a space versus performance trade-off, but it might be a good one for latency sensitive applications. Yeah.
Thank you, Kannan. All right, so let's look at data ordering. Say you want to find all the information about Michael's living in 94085 with the age less than 40. So the query will have to find the zip code 94085 first from your data set and look at all the Michaels living there. And from all the Michaels, it has to filter out age less than 40. So this could be expensive if there are a lot of Michaels living in 94085. But if we add age to the clustering part, all the rows with all Michaels in 94085 will be ordered ascending on age. So finding age less than 40 will be quick, even if there are 1,000 rows, but only 20 Michaels with less than 40, the query executor will immediately stop after crossing the 20 records. So this is how clustering can be useful for range queries. All you have to do is add age to the clustering part.
And essentially, when you add these columns to the index and you have this ascending sort of sort order, essentially all your lookups are very efficient, because we all know that you can search sorted things in logarithmic time, so instead of scanning millions of users or whatever the number is in a particular zip code, now you are actually just going to the place where you start your search for Michael, and you're really narrowing down your search space to logarithmic time, which is like essentially like very efficient.
Sounds good. Right. So incidentally, placing the right columns in the clustering part will also boost the performance of order by clauses because it's already sorted, data is already sorted. So if your queries will want to return data in descending order, if most of your queries, this is how that is what you have to decide when you actually model your index. So this would still work because if the data is stored in ascending order and but you're retrieving in descending order, we have certain optimizations, but it is still better if you define your index with age descending. So to summarize, clustering defines the order within the each chart. Very useful for range clauses with, like, for example, age less than 40 or greater than 40, when especially when age is not in the primary, when the column is not part of the primary key of the table. Remember to add the column to the clustering part if you want to retrieve the rows with order by. Use descending or ascending sort as needed. Let's look at what data partitioning is and how it can be useful. So we have about 6 minutes. So you can split one large table into multiple partitions. Each partition is internally a table and it has its own tablets. With this, you can easily manage large data tables. Very useful for deleting bulk data. For example, you can easily drop older partitions and retain newer ones. For example, if you have you split it, you want just to retain 3 months of data, you want to read it in the 4th month, you can have a rolling window and drop the fourth oldest partition. For scenarios like GDPR, you can place partitions of certain users in certain geographies. Remember, this is only available in a YSQL API and not in YSQL because we have adopted this from Postgres. You can see in this illustration that all IDs in a specific range are in the same partition. For example, in node 2, you have 1 to 1000. Probably if you're collecting data, you collected you associated first 1000 IDs to certain people, and then you feel that that data is not valid anymore, you can quickly drop that particular partition without affecting performance. It's very quick. So partitioning makes data management very, very simple. Also, you can create partitions based on user location so that all your users have fast access to data. You can create one partition for users in East and and place them in East region. So here I have a 4 region cluster. You have one in US, 2 regions in US West and 2 regions in US East. So your applications and users talking to the US East region will access only their data, and so that they'll have very, very low latency. At the same time, people in West will talk to their data only in US West, and they will have a very low latency. So we call this latency optimized geopartitioning. And here in this particular scenario, now you can use the same concept of partitioning to partition your data based on the country of the user, nationality of the user, so that you can place your data of rows belonging to, say, India users in India and European users in Europe. So this is very useful for cases where you want to enforce laws like GDPR. So some final thoughts?
Maybe I just, since we have a little bit of time, I just wanted, I know you had a lot of content, so maybe there are some areas where we had to go a little faster, but I thought this one on partitioning, I'll call out a few important points, I think. So firstly, like you said, Prem, at the end of the day, it looks like one logical table. And this is essentially inspired by Postgres's partition feature itself. And in Yugabyte, I think like 2 common uses of among people that come to Yugabyte. One example I would say is time-based partitioning. Like let's say you have a lot of IoT data, or even you're a finance credit card sort of business, and you're keeping transactions, credit card transactions, right? And you may have a retention requirement, like to keep these transactions around for 7 years or maybe 3 years, whatever be the case. So logically, this transaction history table looks like one table, but underneath the covers, it has many partitions, maybe monthly partitions. So for every month's transactions go into a child table, which we call a partition. And that month's partition itself is a regular table. It could grow into terabytes. It can have shards underneath the covers and so on. But the really nice thing about it is, now that you have these monthly partitions, administrative operations like dropping a partition that's more than 3 years old is simply a simple drop DDL command. So you don't have to run an expensive job to purge data that's older than 3 years and so on. So it makes data management very easy. So that is one use case. And the other use case is taking something like the geolocation column of a table, like the country they are residing in, and partition the data by geography. But you may say, like, okay, why do I want to have different tables for people in different countries? That's where the notion of table spaces comes in, where you can say, hey, table space for North America is pinned to nodes in the Yugabyte cluster that are in North America data centers. And then you can, so we, Yugabyte's table space syntax has essentially extended the Postgres syntax to be able to specify these placement properties to say, hey, I want the table that is for my Europe users to live in a table space that is pinned to servers and zones and data centers that are in Europe, right? So those are some of the common use cases we see of partitioning.
That's very true, Kannan. I just did not touch upon table spaces because I felt that we might not have enough time.
Yeah, I know. It's okay to go a few minutes extra. Yeah, go for it, Prem.
I think we're almost here. So to conclude, so make sure that you understand how your data is distributed or sharded. Be aware of the different parts of the primary keys and how you can best use them. You can use our explain analyze command, standard Postgres command, to see how your query is executed and how the index can be used or improved. I have not touched base on because using explain analyze and understanding the different parts of it. It's a pretty complex topic in all by itself. Data modeling might feel to be time consuming initially, but the initial investment you put in, you will reap a lot of benefits much later on for a longer time. Use partitioning for data management, and using along with table spaces, you can do a lot of magic. Thank you. You can check out our code base on GitHub, and if in case you have any questions, please join our public Slack, yugabyte.com/Slack. Thank you. That'll be all.
Yeah, and there was a question that's come in, but it may be a little bit for a topic of its own. But the question was, can you explain the internal architecture of how YugabyteDB works, and the background processes and memory components and so on? So
that's so you have to look at about 7 or 8 different YFTT topics for this just alone. But you can check out our docs. We have a good explanation on architecture section. So you can understand how our query layer is designed, or how our storage layer. We have a huge section on DocDB, which is our storage layer. You can look at our transactions. We have sections on how the data is distributed. So docs would be a great place for it. So
yeah, thanks, Sandeep, for that question. Like Prem said, at the end of the day, Yugabyte is an OLTP database. It's a transactional database, but designed with elasticity, resilience, and scale in mind. So it's a distributed transactional database that is designed, and we have people. Typically, people might run us on a 3-node cluster, but there are folks like 150-node type of cluster. So it looks like a single logical database that is easy to expand or shrink and be highly available. Can tolerate the failures of nodes, zones, regions. And there's a lot behind the scenes. There's the storage layer, there's the query layer. We support like a Cassandra compatible interface. We call it YSQL. We support a Postgres compatible interface, YSQL. So there are many levels at which to discuss this. Some of the early YugabyteDB Friday Tech Talks cover some of these topics. But our docs, if you just search for YugabyteDB architecture in our documentation page, you'll get a good sense of kind of like a trail to walk through to cover the various topics. And do continue to join us on some of these future talks. With that, why don't we close the session for today? I wanted to thank everybody for joining today, and see you all on another episode of Friday Tech Talk series. So thanks, Prem, to you.
Thank you all. Thank you all. It's been great. But please check out our docs if in case you have any further questions. Thanks, Kannan. Should we hang around?